Good afternoon, everyone. My name is Pranav Vinod, and my advisor for this projects were Professor Scott Peard and Professor Alpha. And the aim of this project is to learn orbital dynamics of binary black hole systems from gravitational wave measurements using something called a neural ordinary differential equation. And we will build on the work that has already been done by Scott Peard, Brendan Keith, and Akshay Khartse. And we will extend their work to include a range of physically viable parameters and different initial conditions as well. So I'd like to start off by motivating what a gravitational wave is and how binary black holes actually produce them. So accelerating the acceleration of a pair of binary black hole generates these massive gravitational waves, which are ripples in the fabric of space-time. Another way to think about this would be to drop a rock on a calm pond. We'd notice all these ripples moving outwards or towards the shore. So the Earth is the shore in this case, and we detect these waves using finite unit detectors such as the LIGO. And generally, the motion of these black holes follow a very complicated path. But in some special cases, such as when the mass of one black hole is so much greater than the mass of the second black hole, the problem becomes one called an extreme mass ratio in spiral. And we will come back to this problem because this is very useful for us. This is the problem that I've focused on in this project, and we will come back to it. So the analysis of these gravitational waves is pretty complex. These gravitational waves themselves are governed by complex partial differential equations, and the solution to these partial differential equations can be traditionally have been found using two main methods. The first one is something called post-Newtonian formalism. The post-Newtonian formalism gives approximate solutions to equations of general relativity, and these are very useful in the case of weak fields. But when the fields are strong, we switch over to the numerical method, which is called numerical relativity. Numerical relativity method uses supercomputers to analyze black holes, gravitational waves, and all phenomenon governed by Einstein's general theory of relativity. The thing about both of these methods is that they are very computationally expensive and time consuming. Specifically, in numerical relativity, they are geared towards just one set of parameters. So you run all these simulations and find results for this find solutions for this one set of parameters, but we can't actually use those same solutions and transfer them onto a different set of parameters. We have to run those simulations again and again, time consuming and computationally expensive. And this is where the idea of a neural ODE comes in. Neural ODEs were not specifically designed for this black hole problem, but we have implemented them here. Before coming to a neural ODE, what does a neural network do, right? A neural network, it maps the transformation between an independent variable, in this case, time t, and a dependent variable y. So if I had to write that down in the form of an equation, it would just be y equals ml of t, and ml is the feed-forward neural network here. Neural ODEs, they model something slightly different. So instead of directly mapping the transformation, they model the dynamics of this transformation. So if I had to write that down in the form of an equation, it would be equation number 2, y dot, which is the time derivative of the function y, is equal to the neural network, which is a parameterized neural network by its parameters and time t. Something to note here is that figuring out the right-hand side of equation number 2 is slightly more complex than it looks. And that is because the feed-forward neural network is already parameterized by its parameters. And in addition, the observable waveform is also a function of time. So there's a lot going on there. But once we figure out the right-hand side, we can use a number of available ODE solvers to integrate the problem and find the solution. Coming back to the Emery model, and this is the model that we'll be studying. And luckily for us, it is a special case where the exact solutions are known. So that helps us while modeling the process itself. And these are governed by equations 3 and 4, which are very complex partial differential equations. And we don't have to go through the entire equation itself, but I just want to point out what the variables are, which are phi dot and chi dot. Phi over here is the angle between the separation vector and the x-axis, and chi is an anomaly which is related to the separation vector itself. The parameters that we'll be varying are P, M, and E, P being the semilattice rectum, E being the eccentricity, and M we'll just set to 1 to simplify our problem. And then F1 and F2 in our case are the neural networks that are used to model the dynamics of the problem. This is very complex, but to simplify it, the image on the figure on the left, which is the trajectory of the small black hole, which is orbiting the supermassive black hole at the center of a system, right? So another way to motivate it would be to think about our solar system, the sun being the center and all the planets just orbiting around it. So that is what we're trying to get, the trajectory that we're trying to get on the left from the gravitational wave data on the right. So we want to get from right to left. And this neural network architecture that we've used is a simple, one of the examples that we've used is a simple neural network with 2 hidden layers, 32 nodes in each layer, and the activation function that we've chosen is the cosine function. We optimize it using the BFGS algorithm and use the RK4 ODE solver to integrate the problem. And just before getting to the results of the actual problem, once again, MD systems parameterized by semilattice rectum P and eccentricity E. Semilattice rectum, think of it as the radius of the orbit. So sun in the center, the P value for Neptune is going to be so much larger than the P value for Earth because it's so much, it's further away from the sun. And prior work done on this project only considered large values of P and large values of E. This project will work on learning the dynamics for a range of P values and a range of E values as well. So the first thing that we did was just run it for a whole range of P values and see what the losses look like. The figure shows the log loss on the y-axis and the semilattice rectum P on the x-axis for a different range of P, E values, eccentricity values. And we can see that for very large P values, the losses are lower. And as we move towards smaller P's, the losses become higher. And the trend remains the same for small values of eccentricity, the losses are lower. And for large values of eccentricity, the losses become higher. So with this information, the next thing that I did was just throw more data at it. What usually happens is for a neural network, if you throw more data at it, it learns better. But that's not what happened here. On this graph, we can see loss on the y-axis and different values of eccentricity on the x-axis, and each line corresponds to a different size of the data set. So for data size equals 250, which is given by the blue line, the losses are much lower than data size equals 1000, which was very counterintuitive to what we had thought to begin with. So to move forward, we implemented something called a cumulative learning technique. In this technique, it's a sort of a batch learning method in that we split the data set into different batches and trained over each batch individually. The splitting of the data set was done in such a way that the first batch only consisted of data points which formed the first orbit of the waveform. The second batch consisted of all the data points which form the first 2 orbits, and so on and so forth. So after training the first batch, we took the network parameters that we had gotten at the end of that training run, and we fed them into the network as the initial guess for the second batch. And the end of the training for the second batch were fed into the initial guess for the third batch. We had hoped that this had worked in a simpler problem before, and we had hoped that this would work well in this complex problem as well. And it turns out it did slightly. So for over here, I hope it's visible. Yeah. So the solid lines correspond to results from the cumulative training, and the dotted lines correspond to results from just static training the entire data set at once. We can see that for large P values, it's at the very end. So for P equals 100, the results are comparably the same. But when we go to smaller P values, we can see that cumulative learning performs much better than just static learning. And that was our first optimistic result. And then with that, we try to see how the network was learning things. So for that, we just plotted the loss versus epoch curve for different batches. And it turns out that batch number 6 actually does not learn a lot. If you look at it, the validation and the training losses for batch number 6, they remain constant throughout all the epochs. Whereas for batch number 1, they they remain constant to an end, but they do go down a couple of orders of magnitude. So this tells us that a lot of the learning for the network actually happens in the beginning for the first and the second and the third batches. And that is information that we plan to use moving forward. Some future work is just trying out different architectures of the network, different number of layers, different number of nodes, and see how that impacts the learning process. We did try a couple of experiments, and for the set of values that we had chosen, it did not impact significantly. So we'll try to focus on regions of the parameter space where it's hard for the network to learn. So small values of P and large values of E, and experiment with changes in activation function, the optimizer, and study its impact on the learning process. And before I end, I'd like to acknowledge Professor Scottfield, Professor Alpha for all the help that they've given, and also a shout out to Brian Cornett. Thank you, and questions.
Any questions?
Yeah.
For the architecture of the network.
Yeah.
What was the motivation behind that? Because it's pretty shallow. So I was curious if you were just focusing like a shorter computational time, because it seems like you've run through a lot of iteration.
Yeah.
But I wasn't sure what that exactly.
So we inherited this network from the earlier work that was already done, and this network performed well for the P and E values that were chosen for that network for that problem. And knowing that it performed well for one problem, the idea was to not tinker around too much with it and just try and see what other changes we could make before actually coming to the architecture and tinkering with that. So I hope that answers.
When you said you used a higher dimension of the data for your initial problem, like did you try to maybe like study why the loss was increasing?
This one?
You said you threw more data.
Oh yeah. Actually, not entirely sure, because that was that was not what I had expected to begin with. In a different problem that I had done before, throwing more data at it ended up decreasing the loss. But for this one, the loss actually increased. So not entirely sure about that.
Any other questions?
Have you done any comparison with the numerical simulations, like how fast this is compared to what? Because that was your overall goal, right?
Yes. I don't think we compared it with exact numerical simulations, in that that would have involved just doing a different process and figuring out building that from the scratch up as well. Did not do that, no.